or you can introduce a current, which I sort of fractured letter, script letter, J, the total current, we call it total current, by definition, is minus, you just have to differentiate here, FCJA times the structure constants, CAD times ABI plus a minus I times partial L matter over partial EJ times dA applied. So you have here, this is the gauge current, This is what I said. And this is that it has a gauge current, it's charged. And this is the matter piece, the matter current. So this is the current of the nucleon in the SO2 feature, and this is the current of the intermediate boson in the SO2 feature. And the field equation written with the total current is then that partial I of F A I J is equal, by the signs which I have here, minus the current, the stylish current, and here we have J. These are the field equations, but you can, the current split into the gauge current and to the matter current. That is also what we do in electromagnetism. And this other current I denote just by J. These are. You have to be a little bit careful with the two different J's which I'm using. I'm just using the literature, and it's done in the literature mostly in this way. So I also do this way. So then you can rewrite the field equation in the gauge covariant derivative. I times F A I J is equal the matter current J minus J times A I. So this is the Young-Mills field equation. This is the matter current, and this is the Young-Mills equation. Where is it? This is the Young-Mills equation if you have here the total current. Yes, but usually we, as physicists, we are used. So the gauge current is hidden in the covariant derivative. If you spell out the covariant derivative, you get the partial derivative plus this term F times C times A. This is just the gauge covariant. So since you have here a gauge covariant derivative, this is where the charge of the current is hidden in this term. These are the Young-Mills equation. And you can then prove that dJ, so if you take the total current, it's partially conserved. It's conserved with the partial derivative. So one has to be careful. These things are sensitive to small errors. F partial I of this current AI is equal to 0. This is the conservation law for the partial current, for the total current written with partial derivatives. For the matter current, you can just use this equation. you get that J covariant derivative of this current J A J is equal to 0. So this current this equation belongs to this, and this field equation belongs to this conservation law. You have the same dichotomy in general relativity, incidentally. You have covariantly conserved currents and non-covariantly conserved currents like this. So this is a political. And if you formulate a conservation law, you always have to start from this version. But of course, one can be transformed into the other. But this, of course, only needs the knowledge of the matter current, and this needs the knowledge of the matter current plus the gauge current. But the gauge current in Yang-Mills theory is not gauge invariant. So it has not a gauge invariant meaning. So this is the same with that. But this matter current is a gauge invariant quantity, it has a gauge invariant meaning. So this is very important. Now my exercise number 2, for those who, for these students which are not yet higher, exercise is fairly also simple. Move the Bianchi identity. The Bianchi identity, it's called Bianchi identity because it's the same structure as identity, as a Bianchi identity in general relativity. So we have, this is a homogeneous, inhomogeneous Yang-Mills equation, and we have the homogeneous Yang-Mills equation, which is E, I, F, J, K, totally anti-symmetric, and here the letter A is equal to 0. So these are the two field equations of Yang-Mills theory, the inhomogeneous one, like the inhomogeneous Maxwell equation. This one, this is the electric current, divergence of the H really, and you have here the inhomogeneous field equation. And the inhomogeneous field equation has in Yang-Mills theory, as it has in general relativity, the status of Bianchi identity. So it's a mathematical identity. Because it follows, you can derive it, and that's how you should solve this example, because the field strength is defined in this way. So you just differentiate the field strength, and you have to evaluate the terms, and you find, if you do it in the correct way, this identity. Just as a reminder for those people, I know there are some people in the audience who know exterior calculus. So in exterior calculus, it goes, of course, in the same way. The L is proportional to FA, H Hodge dual of FA. Metal Lagrangian, and the field strength Fe is equal to covariant, the derivative, gauge covariant derivative of B. There is the potential one form, and the Yang-Mills field equation is the HI is equal Ji HI is equal the star FA, and the Bianchi identity is of course D of FA is equal to 0. So for this Young-Mills equation, linear calculus. One book is Franke, the geometry of physics, Cambridge University Press. Geometry of physics. There's also a student's edition, and it's the second or third edition. I think it's not the third edition. There's a paperback edition. It's Cambridge. Came out something like 1998, like the third edition is something like 2005 or so. No, okay. Now, the immediate impact of the Young-Mills paper was not too big because we have, like in electromagnetism, now a new field, A or E, and this is massless. And you cannot add a mass term because if you add A square, this is not gauge invariant. Like in electromagnetism, gauge invariance forbids the addition of mass square. And for that reason, Pauli didn't publish these ideas. So A corresponds to the massless and there was nobody was aware of that. Some people, Schwiner, shortly afterwards tried to add mass terms. He also gave up, etc. I mean, so this paper was by no means very successful from the very beginning. It's only when symmetry breakdown was invented and all other things that it became more and more clear that this paper has a very valuable nucleus which should be followed up. Well, the section 3.5 immediately Utiyama then generalized it to all semi-simple Lie groups. I mean, this is what I said. We have this, we are not, the whole idea of Young-Mills was applied to SU2 because he found isotopic spin in nature. But obviously, Utiyama didn't care too much about nature, and he immediately generalized it to all semi-simple Lie groups. So in particular, to SU3, etc., entire unitary symmetries, and to the Lorentz group. And this was new, and this was, of course, very remarkable because then he again tried to include gravity, which was included in Wein's paper right from the very beginning. So 3.5, and you should recall that SU3 as a group in physics was only discovered 1961. We are here 1954, and Utiyama 1956 was a paper published. So 3.6, Utiyama's generalization. Utiyama's generalization to SU3. It's just because after SU2, obviously SU3, and any semi-simple Lie group. Why semi-simple? Because these are the groups, Lie groups by definition, where the structure constant, the determinant of the structure constant is, I mean, of the Killing metric of the structure constant is unequal to 0, so it's non-degenerate, and then you can play all the games which you can play with the metric, you can invert it, and you can invert, and you can develop a tensor algebra for these expressions. So this is what physicists can handle, and for that reason, Utiyama took these groups. As I said, this was 1956 paper, and if you read the paper, it's very similar in spirit to what Young Mills wrote, just that the formalism is a bit more heavy, and I'm not going to develop this in any detail, because what I did for SU2 I could not do for SU3, and it's just the same equations which I would write out just in favor of this 3 times 3 matrices. I had some 8 times 8 matrices and other things, the Gell-Mann matrices and other things, which doesn't bring me nearer to gravity, and for that reason I will not go into many details. I should also underline that Young Mills and Utiyama both work in special relativity. So their underlying space-time is special relativistic. Weil had already as background general relativity. So in Weil's theory, general relativity was already encompassed. In those theories, it was not. But the idea which they took from general relativity, that these interactions cannot propagate with infinite speed, this was the general relativistic idea which they used. So let me turn then immediately after these few remarks no, this was 3.5, I'm sorry. 3.6, I make a little bit more remarks about Utiyama and gravity. Utiyama and gravitation. So what I mentioned was that he, as one example of a non-symbolic group, he took the SO13, and he had a section in his paper which was called Lorentz group and the gravitational field. Now, it was noticeable that he had to change his formalism quite a bit in order to accommodate the Lorentz group. It was clear that he had to do a lot of work, and it's not always very transparent what he did. I mean, there is certainly the merit of Utiyama that he was the first to point out, after Weil, that the gravitational field has some relation to the Lorentz group and is related to gauge hypothesis. I think there is no doubt that Utiyama saw that very clearly, and this you can also find in his title. But on the other hand side, in this paper, there are some things which are not very satisfactorily solved, and I will just list them. That's not in order to make this, to say that this is a bad paper. That's not my goal. My goal is to analyze the paper, that's what I did, and to find out whether what he did with respect to the gravitational field is satisfactory or not. And I found out, and it's not my only, Kibble and Sciama found out that it's not satisfactory, that one has to extend it. So, since in our book we reprinted, of course, the Utiyama article, there you can follow up all these ideas. So I have basically 3 points why this is insufficient. First, 3 points why Utiyama's approach to gravity was not completely satisfactory. these reasons are, first of all, there is in his whole paper, Utiyama used coordinates. Now suddenly he introduced frames, and he gave really no reason why he did that. Introduction. Of n-holonomic frames without convincing reasons. So suddenly in the paper, when he turned to gravity, he introduced frames, and he applied then the application of the Lorentz group to these frames. Application of SO13 to these frames. And then, of course, he made the gauge idea. Then he, what he did then, he found out that there is a 3-index symbol. The Lorentz transformation has 6 parameters, so 3 boosts and 3 spatial rotations. So you need 4 times 6, 24 potential for compensating. So he has 24 compensating fields. And then he compared it with relativity and found out that this doesn't match, and so he has to do something. So he, and that's now the second thing, he assumed a Riemannian space for the compensating fields. For the compensating fields. Without reason. To say to this, of course, you have, we reduce this, so to say, to the Christoffel symbols. The Christoffel symbols determined from the metric. So what he introduces in, he has these orthonormal frames, he constructs the metric, he constructs the Christoffel symbol, and then he assumes the space is Riemannian, and then he can link this to the Christoffel symbols. And so he gets rid of certain degrees of freedom which he cannot use. And the third reason, which is perhaps for me the strongest reason, the current coupled to SO13, the current coupled to SO13, coupled to SO13 is angular momentum. Not the ordinary current of GR. We know that in general relativity it's energy momentum, which of course is related to translations, but since he starts with the Lorentz group, he only finds this current. And he makes also a remark, and now I have a third exercise for the student, because the other ones were exercise number 3. Extract from Utiyama's article, extract from Utiyama, put it now, the reference physical review. 101. No, I think it was not D at this time. Was it? I think it was maybe 101. 1597, 56. From footnote 7, this is done, this Riemannian assumption in footnote 7, and identify the contortion tensor, which we identify the contortion tensor, which we discussed in the first lecture, the contortion tensor. What does